Wasabi, you guys. Welcome to Integration Bee Training for Advanced. This is part 18.1, which means that I'm going to be introducing you to Euler's reflection. Now, what on earth is Euler's reflection? If you remember gamma function, right, it is definitely to do with the gamma function. And it is an identity with the gamma function. And the gamma function looks like this, right? Kind of like pretty much a factorial function for real numbers, in a way. So, oh god, I feel like I just triggered a lot of mathematicians there. But gamma of x times gamma of 1 minus x is equal to pi of cosecant of pi x. This is Euler's reflection formula. Okay? And this is actually the same thing as, if you put it in beta function form, it's x 1 minus x. Okay? That's the beta function form. And this, you'd be very surprised how useful and how, this is a lifesaver. And a lot of advanced integrals that comes up in integration bees, you'll be kind of like thrown with this. So, or an integral where you're going to need Euler's reflection. Okay? But for the sake of this video and this section here, I'm just introducing you, just getting familiar with this formula. Okay? There is another formula that I do want to point out, and that is where you have 1/2 plus x gamma of 1/2 minus x. There are some times where you'll end up in this formation. In this case, this is equal to pi secant of pi over x. Okay? And of course the beta function form, that's what you think it is. Okay? Alright, now let's go ahead and get straight into the integral examples. Let's start with this integral, because this is a very common reoccurring integral. Every speed integrator must know how to integrate this. Okay, so what on earth is this? The ln of gamma function dx. So this actually, it's a very popular integral. It comes up a lot in integration bee. It's called the Rab's integral. And I don't know if I'm pronouncing that correctly, but you can literally type it out if you type in Rab's integrals, Rab's, Rab, Rabe, I don't know. But that's how it's spelled. Rab's integral or Rab's integral. But pretty much it is a log gamma integral. And how do we compute this? Very simple. Sneaky, but simple. Use King's rule. From 0 to 1, right? This is the same thing as the gamma of 1 minus x dx. And now you already see it. Oh, aha. Right. If you add these two together, right? That's 2i, so it's a half. From 0 to 1. We get ln of this times this, which by Euler's reflection, we have pi cosecant pi x dx. Okay? And so now what we have here is we pretty much have a half of what? We can take the ln of pi out. So we technically have ln of square root of pi. And then we have minus, just to kind of simplify further, minus 1/2 from 0 to 1 ln of sine pi x dx. Okay? Cool. And if we just, for simplicity's sake, let's just go ahead and u sub that. Ln of square root of pi minus, it would be what? this would be 1 over 2 pi from 0 to pi, and ln of sine of x dx. Ah, doesn't this look familiar to you? Right? However, we know this integral if it's pi over 2 at the top, right? But I mean, that's not that hard though. We can just simply use Queen's rule to manipulate that, right? So, in other words, if we use Queen's rule, I'm just going to do it mentally, right? If we let x, let u equal pi over 2 minus x, we'll get pi over 2 here, and negative pi over 2 here. And then we can utilize symmetry because it'll turn out to be cosine of x, and then we could do the same substitution again. So now it would be 1 over pi, and now it is simply from 0 to pi over 2 ln sine of x dx. Okay, and so now what we have, our answer is ln of square root of pi, right? We've solved this before. It's a very common integral that honestly you should just memorize it because this is so reoccurring. It's as popular as integral of secant cube. Like, you should probably just memorize the answer because it's so reoccurring. But if you don't remember this, it's in our Queen's rule integral, our Queen's rule video. Sorry. So this is the answer to this was 1 over pi. It was pi over 2. I'm sorry, negative, so it's be positive. Pi over 2 L of 2. It cancels out. It's also a square root of 2. So our answer is the ln square root of 2 pi. And that is the Rab's integral. Okay? So the integral from 0 to 1 of this log gamma here is equal to ln of the square root of 2 pi. Okay? A very common integral. Every speed integrator must know this. Okay? Let's do another example. So now how do we solve this one? Okay, so I made this integral just for the sake of this video, for practicing purposes, right? Notice that if the gamma of 1 plus x, right, it works like factorial, okay? If you remember, the factorial version is x minus 1 factorial, okay? The way factorial works is like x times x minus 1, x minus 2, whatever, which still equals x times x minus 1 factorial. In other words, x plus 1 is equal to x gamma x. Aha! So we can substitute this with x gamma of x. So that x is going to cancel out here, and that gamma of x with gamma of 1 minus x, Euler's reflection. So what we have now is 1/3, 1/2, and now we have Euler's reflection, which means that we are left with pi cosecant of pi x dx. Okay? All right. So now, let's go ahead and integrate this simply. I mean, you could just let u sub the pi x just to simplify this. Pi over 2, pi over 3. Right. This would be, I think the pi goes away. Yeah. Cosecant of u du. And now this is simply ln of cosecant of u plus cotangent of u from pi over 2 and pi over 3, right? 1 over sine of pi over 2, that's like 1 plus 0, so everything's going to be 0. And then if you plug in, so minus is going to be, so minus negative, that's going to cancel out. So now what we have is ln of what? Cosecant of pi over 3? What's sine pi of 3? Root 3 over 2, so 2 over root 3 plus 1 over root 3. Oh wow, would you look at that? So our answer is ln the square root of 3. Okay? All right, perfect. Let's go ahead and do just one more example. All right, so this is our last example. I'm honestly kind of proud of this integral. It's probably one of the coolest integrals I've made. I don't think I can ever make another integral like this, but so I wrote this integral for Cambridge University integration B, and it's actually quite a simple integral, not too bad. So there's something suspicious here, right? We have exactly pi cosecant of pi x, exactly pi cosecant of pi x here. So it's very suspicious. So what do? We convert it into gamma in terms of gamma functions. So we have dx gamma square plus gamma and then gamma 1 minus x. Okay? And now let's go ahead and factor out gamma. And then we have gamma of x plus gamma of 1 minus x here. Okay? Now, here, I want to label this. Let's label this A and label this B. You already know where this is going, right? You already know where this is going. This is now equal to from 0. That looks like a B. That irritates me. 0 from 0 to 1. We have dx. We have A times A plus B. Right? If we use King's rule, what happens if we use King's rule? Then this becomes 1 minus x. So now we have B, A plus B. Okay, let's combine these two. Then we get 1/2 from 0 to 1. We get, let's factor out A plus B. We get A plus B times 1 over A plus 1 over B. And what happens is now we have half of the integral from 0 to 1. We have A plus B. This is AB, A plus B. Oh my god, this cancels out. And what is AB? What is AB? Do you remember AB? AB is gamma of x times gamma of 1 minus x. Wait a minute. It's the Euler's reflection again. So what we did is we did a reverse Euler's reflection and then used the frontward Euler's reflection. So we went reverse and then back to forward. So now our integral here is now, this is what? Dx over pi cosecant of pi. So pretty much we have sine pi of x over pi dx. Okay? This is now equal to 1 over 2 pi of negative cosine of pi x over pi from 0 to 1. Plug in 0, it's like we get like negative 1 over pi. Plug in 1. We get 1 over pi because cosine of pi is negative 1. So in other words, we technically have 1 over 2 pi times 1 plus pi plus 1 plus pi. This is 2 pi. I'm sorry, 2 over pi. So our answer is 1 over pi square. Okay? That's a 1. So our answer to this amazing, beautiful integral here is 1 over pi square. Okay? Alright, very cool, right? Again, don't forget to, dummyfy your functions. You can do this so that it's just a lot faster to write. Okay? Alright, that was an amazing integral. I don't think I can ever make another one like that where you use the reverse and then bring it back. Alright, so that is it. I hope this was fun and amazing for you guys. I think a majority of you guys already know what Euler's reflection, but I just want to, again, just for those who haven't, I'm just introducing this Euler's reflection. and some very nice integral examples too, to help kind of introduce it. Okay? All right. Are we going to do with more Euler reflection with this? Yes, we will in the next video, so stay tuned. All right? And as always, practice and try out these integrals on your own. So I hope that helps. Thank you so much for watching, and I'll see you guys in the next part.